Good morning. Welcome to this session of scientific computing. I'm Fan Zhenxiong. Our first speaker is Professor Bai from University of California, Davis. Professor Bai is very famous, and he is a computational mathematician. His research interests are applied numerical linear algebra and matrix computations, iterative methods, software development, and high-performance computing. The title of his talk is Advances and Challenges in Algebraic Eigenvalue Problems. Let's welcome Professor Bai.
Thank you. Thank you, the organizer, the chairs. Also, I would like to begin with the sincere thanks to the organizers for this very distinguished honor. It's a kind of a little bit frightened, say, to give us a talk to at such a conference. But now I feel very comfortable be here because most of you are the young people. I assume many of you are students. And so this is exactly types of platforms I would like to talk to and communicate with, etc. So you probably Google me and you will find, or Baidu me, you will find I'm has been working this field for over 40 years. I was the first of a college, entered the college after Cultural Revolution, 1978. I started at my undergraduate study and did all my bachelor degree, master degree, and PhD in China. After that, I went to the US, did a postdoc, and continued of that. Okay. So today at this conference, so I would like to talk about, since I'm in scientific computing, so I selected this topic, so-called algebraic eigenvalue problems. So since when I accepted this invitation, so I look at the audience and very broad, so I give a very broad title also in terms of so-called advances and challenges in algebraic eigenvalue problems. Of course, once you started prepare the actual talk, this field is just too big to try to ambitiously cover them. So that's why I added a little bit more focusing on more recent development. So I say the algebraic eigenvalue problems is a cornerstone of scientific computing. Here is exactly 60 years ago with the publish of this book by the Jim Wilkinson in 1965. 60 years ago, exactly to this day, essentially to this year. It's formed the foundations of the cornerstone. If you say when this cornerstone is completed, this is exactly this book. You can consider this field and this topic thematic as a cornerstone, because this book is considered as one of the most classical of books in scientific computing by all aspects. Because Wilkinson was a student of Alan Turing, and when he was after his college degree, he went to work for Alan Turing as his assistant. He never got his PhD, but eventually he was a professor at Oxford University and also the fellow of the Royal Society. In today's term, basically just talk about the academicians. He works with Alan Turing in a very early generation of computer, doing all sort of computing. So this is exactly, he totally wrote two books, and and of course with all the publication, etc. So as since this page has been here for a while, it's showing earlier, some of you may read and already have read it. And you find it's a fascinating topic to him, and also very deep. The algebraic problems, it seems very simple. It's very easy to define. It's not like some field of mathematics. It took enormous sort of background terminology, etc., to define this problem. But algebraic eigenvalue problems, just like many matrix problems, are very strictly very simple to define. But on the other hand, it's a very amazingly and deeply connected with many branches of the numerical or mathematics and also computing. So this is the book I basically formed foundation. You probably also noticed This has a Chinese translation of that. This was around the 2000s in 1999 or 8. So things that I'm talking about the Wilkinson. So Wilkinson has two books. So this is a couple of years earlier, he wrote another book. It's called Running Error Analysis in the Algebraic Process. So this book, so in China, was translated in 1983. So these books, when I was a graduate student of just finishing college, because that was 83 published, I paid 82 cents, bought this book. I still kept them and with me and references from the time to time of them. So why this book is last year was reprinted by the SIAM. You think, after 60 some years, running error analysis has been advanced in an enormous of progress. Why still printing them? Because this has a deep, deep connection with many of today's the AI, high performance AI type of machines. For example, we all know this NVIDIA's the chip provided the backbone of AI, machine learning, etc. So if you're looking at those chips, looking at this challenging how to from those chips facing the of a high performance computing or AI machine learning, and you go back to exactly around 70 years ago when the initial of a computer, electronic computer started, and within all those issues, how to represent the numbers. And Wilkinson in this book talk about three types of presentation of number. Because today you use MATLAB, etc., you don't pay attention. You're all using a uniformly so-called a floating point representation. But in the earlier days, the computer using a floating point or fixed point, and also something between the floating point and fixed point. This is called a block floating of that. So if you're interested in this field, interested in such amazing development, you will find that NVIDIA chips or just announced the H200 sales to China, or latest this Blackwell 200, exactly need to deal with a fixed point and deal with a block floating point operations again. So in other words, histories, people often say, of course, repeat itself, but of course it is not in the same state. But anyway, so I just using this to do this of that. So things a little history. So that's the all I wanted to say about the algebraic eigenvalue problem history of that. So in today's the terminology or classification or taxonomy, and then the algebraic eigenvalue problem roughly can define in these three categories. It's very straightforward. The first is so-called linear eigenvalue problem. Namely, you give me one matrix, or you give me a pair of two matrices, A and B, are all the constants matrix, the square. Or you could be rectangle. There is a rectangle eigenvalue problem you can define too. But nevertheless, the key is you need to find a vector x and a scalar such that the a times x still is equal to x, but only up to the scaling difference. So this scale is called the eigenvalues, x called the eigenvectors. So this is a linear eigenvalue problem. This is exactly Wilkinson's basically the book is focusing on. As you can see, it's so simple. Give you a matrix A, find a vector x and lambda to satisfy. But that book is roughly about 700 pages to discuss the up to that stage and how to deal with this type of problem. But within the advanced things that you may call the Wilkinson stage, so now we also increasingly to this so-called two kinds of nonlinear eigenvalue problems. One is so-called with respect to eigenvalue is nonlinear, because this is considered as a linear, because although, mathematically you probably say this is nonlinear also, because x and lambda are both unknown, so they're in nonlinear form. But if you separately, so they are both respected to eigenvalue are linear. That's why I call it a linear eigenvalue problem. Okay, so this is now nonlinear is in a sense it's it's no longer linear with respect to the eigenvalue. It's nonlinear with respect to eigenvalue, but eigenvector is still linear dependent. So this class is called nonlinear eigenvalue problems. We just say MEP in short. Okay. So now there is another class of widely appeared eigenvalue. But so those are all the example. You can just think about what's the nonlinearity look like. And of course, each of them connected within certain types of background. For example, the last one, if you study the different delayed differential equations, and you're looking at the stability or the rate of delay, etc., you need to find such eigenvalues. The third class of that we call the nonlinear eigenvalue problem. But now with respect to eigenvector is nonlinear, because in this case, you are looking for an eigenvector x, but this matrix itself also depends on the x. Okay, so eigenvector itself, as you clearly see, you would need to find both lambda and a vector to satisfy of those. So, for example, the first one, if you some of the students remember you studied give you a matrix. I want to find a numerical radius of that matrices, and it's eventually can formalize in terms of such nonlinear eigenvalue problems. And this is another very simple, super simplified model, just one particle, the so-called Khongshan DFT equation from the electronic structure equation. I will give you the full representation later. Okay. So anyway, so this is three class of the nonlinear eigenvalue problems, algebraic eigenvalue problems, because they are all just depend on the matrices you give to me, and some of course associated some parameters. So since my title is called Advances in all those eigenvalue problems, so I thought about how to talk about this. So then for the first two, I want to demonstrate that there are still an active research problems. I picked the two examples to demonstrate that each of them, where their problem coming from, what are the challenges people are facing. Certainly, that's not a coverage of all the development, because there's lots of other people's work, etc. I cannot deal with. The third topic is so-called eigenvector dependent linearity, nonlinearity. This is relatively, although the problem is defined in the 60s, since the Khongshan equation essentially is a nonlinear eigenvector problems. But as an algebraic nonlinear eigenvalue problem, that's only in the last 10 or so years, people have actively focusing on this class of that. So therefore, I will try to cover them in a little bit more wide range of that. Okay. So the first, give you an example, the recent development of linear eigenvalue problems. That's considered as the simplest. So this is a joint work with a student Zhaojun. Right now, he's a graduate student at the EPFL in Switzerland, and also Wenbing Chen, he's a professor at Fudan University. So this is a very simple eigenvalue problems. Let's say I give you two matrices, symmetric, and even I assume that it's positive definitely for simplicity. Okay, and then you all know that by simple linear algebra, you know all the eigenvalues are real, and you can order them. And since both are positive definitely, you also know the smallest eigenvalue must be non-zero. And then all those U are the corresponding eigenvectors, and we assume they are normalized, etc. Then associated within this eigenvalue problem, there is a very important quantity so-called Rayleigh quotient. And this is a quantity defined by this ratio of this quadratic form. Okay. So why this Rayleigh quotient are very useful? The reason is that if let's say we are only interested in the smallest eigenvalue problem, that's also in practically many real life problems, then you can show the smallest eigenvalue province must be the smallest of the values of this Rayleigh quotient. Okay, so this is the so-called and the corresponding we call the argument and the x achieve this is exactly eigenvalue of that. So therefore, this is basically all the background you need to know about this types of eigenvalue problems. So as I say, this is a very classical. Wigginton studied this types of that more than 60 years ago. And then afterwards, people continue, or even before that, because some of literature regarding this class of problems is back to 50s. Because as you can see, linear eigenvalue problems, the easiest or most straightforward method is so-called power methods, and also associated inverse iteration method. But you can put those in a term is so-called preconditioned eigensolver. Namely, you are using this simple recursion. This is xk is your current approximation to this smallest eigenvectors. And then this is rk is the associated residual. Okay. And then you can using this simple iteration, you pick some sort of we call a preconditioner. If you don't say I don't use preconditioner, you use identity matrix, then you are executing so-called of this steep descent because every time you're looking at the residual direction. Or if you're picking a preconditioner just as matrix itself, we say you are running a so-called inverse iteration. Those are all the fundamental methods. But in general, you can looking at this types, etc. So this is also today called the preconditioned inverse iteration because it's generalizing the inverse iteration. And the other is you can also, the other class of a preconditioned eigensolver is called a locally optimum. Namely is that you try to minimize this Rayleigh quotient, okay, let's say because the minimum is associated with the eigenvalues you want it. And then you each time you are looking at this smaller dimension, basically based on the current previous one and also precondition the residual vector. So you are in this three-dimensional subspace and looking for what's the optimal. That's so-called a locally optimal meaning. Okay, so those are the class of that. So this is the methods, and way earlier is but systematically studied by mostly the Russian mathematicians back to 40s and 50s. And Samakirch is the one of name wrote a sequential paper. In the 19th and 1990s and the 2000s, and Kanyashev, etc., wrote also sequence of paper, including this young fellow Ming Zhou. He's still in Germany. But then Yunfeng, he is now at your institute. He and I, within of our collaborator in of a field of computational physics for electronic structure, we're also looking at this so-called preconditioning steep descent, basically a variation of this type of method, and try to prove its convergence analysis, etc. So even of that. But most recently, people get back to this classical and simple method again, revisited them. So there is quite a few publications. So today, I want to just briefly summarizing some of our latest work on this. And this was just published earlier this year, but of course, finishing last year. So what this method is so-called a locally optimum, is right. That's the outclass because there is another famous one. If instead of single vector, if you change it to block vector, this is called a log PCG. It's basically it's a default method now people using in electronic structure calculation. This is a simplified version. So what this picture shows, there's all those pictures to show is a different class of matrices. Okay, so those are all the different class of matrix coming from the different application and different background. We don't need to know them. So if you are running this method, as you can see, the convergence, there's the two curves, each color, let's just focusing on red color for now. So red color is show you this convergence of eigenvalues and eigenvector. as you can see, overall, this is just an error. Okay, so it should go down, etc. As you can see, they are proportional. That theory knows that eigenvalue, eigenvector, that the convergence rate are roughly the same. But on the other hand, they are roughly of that. Okay, so all this, some of them go fast. There are some exceptional cases, seems very slow, but or you might call it non-convergence after a certain number of iteration. So therefore, this method has been of that. Furthermore, people believe this, if you properly define a so-called condition number of this province, then they're using a quantity to characterize the difficulty of this province. You roughly see this rate of this is a convergence rate about of a square root of a reciprocal of a square root of a condition number. Okay, so why this method better than you just the simplest the steepest descent? Because the steepest descent is just the reciprocal of a condition number. Is right. This is the square root of condition number, so therefore certainly that big speed up of that ratio of potential relation. But unfortunately, because this method has been at least formally presented in this form is back to 90s, but it has never been formally proved in its converging in square root of condition numbers. Okay, so therefore it's only a conjecture. And although through the different mechanism and the related work, etc., and is a conjecture of that. So what in this work and etc. So what we have done is that to try to provide a so-called provable of a convergence of this. Namely, is that we will try to develop a method which is a performance. This is basically the blue line you saw here. Essentially, the performance is similar to the log PCG, but what's the advantage of this? Of course, we can prove this algorithm indeed is convergence is at the rate of the square root of condition number. Okay, so therefore, in terms of algorithmically, you might call it we are not proposing a new method or a new method per se in terms of speed up performance. Of course, the execution steps is different. Okay, but nevertheless, essentially we call the provable of this. So what this doing, the algorithm essential idea, just go through the idea, okay? So as you can see in earlier, we try to minimizing this of radial caution, as you saw that earlier. But now what we do is that we define a new objective function. So for any current approximation, you define it as a so-called projected space. Okay, so this is all those transformation. Don't worry about that. So basically, is if you're looking at this, you at the current approximation, you're looking for next one on this. If it's a two-dimensional, is on circle or in this on the sphere. And then instead of direct looking this next best, so you first project this problem to another space, okay? And then on this space, it has a nice property. It's a convex. You can prove this projector through this projection is a convex. And furthermore, this function after this projection or mapping is also a convex. So in other words, the entirely the province now you define is a convex optimization province. In other words, it's much simpler than the original of that. Okay, so this is just to say through the of that detail you is let's say if well, let's just skip. So now the idea is essentially you have a convex optimization now. So at this stage, you can shifting your gear towards another of a very related people study convex optimization. Because for convex optimization, you can just think about a convex, both a convex objective and convex set. There is a so-called Nesterov accelerated gradient. Namely, is some sort of a gradient flow province. You can associate it with a certain gradient flow province, and you can show if you define this through this so-called Lyapunov function, you can prove this gradient flow is exponentially decades. In the sense of solving this the gradient flow problems, you can get the gradients of a guarantee of that convergence and at the rate of um, using this t of time steps. Okay, so this is essentially of a it's another sort of a subject. People study gradients flow and how to connecting with the optimization. If some of you follow the optimization, you will find that that's people study as well. So here I just summarizing the results primarily in this Chen Long and his students recently published in the best programming. So within this, now you can discretizing this. Okay, so this is gradient. You can use, we call it like a, you can use Euler, forward Euler, or backward Euler, implicit Euler, etc. There's a mixture, so-called a semi-implicit Euler scheme. But the difference is that we are trying to make sure it's sufficiently decreasing, guarantee a monotonically decreasing of your objective function. So we sort of modify the third steps in this algorithm. And then up to that, we can rigorously prove the objective function is monotonically decreasing. The second is that if you are going to using the time steps, okay, so you're picking the proper time steps within the proportional to the condition number, you can show it's the convergence rate. It's at this step size, but this step size in optimal sense is the square root of condition number. So therefore, you can show this scheme if you are using them for solving this gradient flow or associated optimization problems. It's a convergence rate at the square root of a condition numbers. Okay, so this is basically essentially you might just say we are following the results and the tool from there. But of course, the twist is that all those schemes is in this projected space. But in our actual calculation, we are in our usually the so-called Euclidean space, is right. So we are in the IM, the Euclidean space. So we need to matching the properly the condition number you design here to so-called a call precondition for this matrix A, because in this space you're working with this matrix, so-called projected matrix. Of course, all those Q, but orthogonal Q is never formulated. It just mathematically is in the background. And then afterwards, you can rigorously show the radial quotient is going to be strictly decreasing and so on, and also convergence rate, etc. And you can study the condition numbers, and if you properly conditioning and etc., then you can show it. This is a typical rate you will see in the gradients of flow types of steeps to gradient types of turns. Now you are preconditioning them, and then the step size can be chosen at the square root of the condition number. So we basically sort of through the detour, and then we can prove this method eventually just a sequence of a recursion. It's also just like a log PCG method. It's a very simple recurrences relation. You can prove then it's at the square root of that. Okay. So and then this is what you saw this here, the behavior of this blue curve. So in other words, essentially, if you accept some exceptional cases, otherwise, as you can see, these two methods are essentially the same. The only difference is that this method we can rigorously prove it's a convergence, etc. Okay, so yeah, in fact, I just suddenly reminds me. So Liang also did some of what is convergence of that. His setting is more complex than my settings here. He tried to do this using a log PCG type of methods, etc. But this is just some simple form of that. But anyway, so this part of the work, I tried to show you even some of very classical of an eigensolver for very simple linear eigenvalue problem. So there's still quite a bit outstanding research challenges. Of course, the efficiency interpretation is one matter, and also theoretically how to prove some popular, widely used type of methods in terms of convergence, etc. Okay, so this is essentially of that. I think that this is basically of all those papers I cited here. The last three of them, are essentially of three of them are quite a recent work on this type of classical method. People try to prove them in a mathematically rigorous sense. Okay, so this is my first selected topic. My second selected topic is on the second kind of nonlinear eigenvalue problems. So this is so-called eigenvalues dependent nonlinear eigenvalue problems. Okay, so this work essentially goes back to another very classical paper. Many of you, if you studied this field, doing the numerical analysis, particular study of the numerical linear algebra, etc., either your advisor will tell you or you will quickly figure out, just like every field always have some very classical and long ago published, or you might say forgotten by the people. But once you get deep into it, looking back, you recover, oh, those things are exactly have been studied, etc. So here is a paper, sort of you might call it published 50 years ago, and some 50 years ago by another leading figure in this field. He called it's a Science Review article. It's called some modified matrix eigenvalue problems or algebraic. So in this field, in this paper, he surveyed the 7 different types of eigenvalue problems. And let's just focus some of them, 50 years later, already has book written on it. For example, total least square problems is by itself now is a field of that. There's a couple of books written on it. Okay, so just looking at the first one, it's a very simple. Again, it's a very just like many of the matrix problems. It's very easy to define and understanding what it is. So this is essentially really Gaussian, and which assume that normalized because really Gaussian is homogeneous with respect to x. So now only difference is that we added this constraint. It's so-called homogeneous constraint. In other words, x has to be living in the null space of this matrix. But of course, if you don't have this constraint, this is just really Gaussian. This is just I was talking about in the linear eigenvalue problem. But now you added this constraint, as you can see, you have to do some, additional work to how to handle this. So now so this, of course, in this paper, it's already addressed and how to handle in this and what's the development and how to connecting with other. And later on, there's a few more papers written and how to addressing some different aspects. But let's just change this problem slightly. So instead of homogeneous, instead of equal to 0, living in that, we just say it's living, it's no homogeneous. In other words, it's equal to another vector. In other words, you think about it as a hyperplane, is right? So essentially, you just change this. So this problem now is defined in this form. Okay, as you can see, B is just a non-zero vector. Of course, if it's 0, it's equal to we Gauss studied. Otherwise, it's non-zero. So this is what we call the constrained Rayleigh quotient. Basically, this part is standard Rayleigh quotient, but now you added this constraint. It turned out this very simple. If you do a bunch of the equivalence transformation, okay. So for some of you probably see some of transformation before, but again, for the time being, I'm not able to go through each of transformation, equivalent transformation rigorously. But it's just fascinating. In the end, you try to solve this, you actually end up a nonlinear eigenvalue to solve. Because in this case, as you can see, your eigenvalues you're looking for is satisfy this relation, but with lambda is square, is right. If you multiply it out, it's lambda square. So in other words, it's the so-called quadratic eigenvalue problem, or QEP. Okay, it's a quadratic nonlinear eigenvalue problems. In other words, you try to solve these problems. Now you need to do is solving this so-called quadratic nonlinear eigenvalue problems. So this is our first is a transformation, but of course the second is you have to rigorously prove, and they are all so-called equivalent. I think. Oh yeah. So this is a different bunch of the theory you need to prove them they are rigorously equivalent. Okay, so you don't need to worry about that. But now let's focusing on this quadratic eigenvalue. So first you are quadratic, and then as you can see, you are looking for smallest eigenvalue. But in general, quadratic eigenvalue, even all are real or symmetric, etc., they could have a complex eigenvalue. In other words, essentially, you are for the smallest, leftmost eigenvalues, you need to rigorously prove whether you need to the eigenvalue, the leftmost, whether it's real, and whether the solution corresponding the leftmost eigenvalues are indeed is optimal of that. So those are all can be rigorously proved. You can prove this and of a so-called of that. So this is it's not too difficult. It's just a standard linear algebra transformation. But the implication is that once you have this simplified quadratic now, you can using this our well-known algorithm. This is the case so-called an Anschutz algorithm. You can preserve. You can only working on this matrix H, and then you can preserve the structure, and you are solving exactly the so-called of the smallest eigenvalue problems, etc. Okay, so this is essentially is the more show you the nonlinear eigenvalue problems. Essentially, first where they might coming from, that's of that. The second to show you is that sometimes often those nonlinearity has certain structure. So how to preserving the structure during the solution process is critical. So quickly of a background or the payoff you are using this types of benefit to using this. I'm using this classical, this so-called clustering method of problems. You have a set of the of points or vertex. You want to cluster them into a subset, and each of the subsets are very strongly connected, and the different between of them are weakly connected. This is just a standard clustering problem. And one of the popular method, which is invented around 2000s, is so-called a normalized cut. So normalized cut is just to try to define of a quantity in a relatively of each of those. So of each set, how they want to make sure between the set are weakly connected and within the set are strongly connected. This is a quantity so-called normalized of this. But then through the bunch of algebra, you can show this is nothing but the optimization of this trace of this so-called Laplacian matrix. Again, for some of students having background in this, you will find that that's a pretty classical by now. The difference, but unfortunately, as you can see, it has a very some success. For example, if you define those point classes with 4 different points, you just using the general geometry, Euclidean Gaussian distance between all those points, and you can find it's recognizing each of class pretty well. But on the other hand, if you have those images of that enter to this, as you can see, you're really interested is separately this camel for the rest. But as you can see, this is very poorly separated. So people solving this, of course, have different techniques. And one of the very algebraic approach, or very people call it using some a priori information, essentially you can enter during the process that you call this like semi-supervised learning. You can basically say, I provide you some points. I tell you all those green dots must be in one set, and all those blue dots must be in another set. And green and blue cannot be connected. I just provide you roughly about a couple of dozen such data sets, which means that during the point, the separation, besides your normal doing these things, I tell you certain points of set must be within the same set, and this other bit must be in another set. So in other words, last two of those I just provided some additional information. As you can see, once you have this, it's instantly you will get a very nice segmentation of these imagings of that. So this is so all those constraints, if you write down them in our algebraic term, it's exactly this nonlinear constraint, non-homogeneous constraint, sorry, not nonlinear, it's a non-homogeneous constraint. So this has been the payoff, as you can see. Let's just looking at the last data set. So total number of pixels is about 1 million, okay? And a number of that. So I provided you about 30 points, tells you all those blue, all those green dots, etc. So now it's just me, just a regular laptop. It takes about 1.5 minutes. It can get the segmentation of these flowers and from the rest. This is the corresponding eigenvector you calculated. So if you're using some other methods, and it's roughly, as I say, references point is about 30 minutes. That's the best timing results we have. And of course, when the people in this computer vision study this type of problems, that's around earlier 2000s, and this take about 3 hours to partition such segmentation of this. So this is essentially of a pay. I just illustrating even some of this nonlinear eigenvalue problems, where they're coming from those seemingly unrelated problems, okay, imaging segmentation, but turn out to be an interesting nonlinear eigenvalue problems. And once you know this nonlinear eigenvalue problems, you explore the structure, and then you can really benefit of the computing, etc. So, so of course, the same problems can be formulated in some other way. Okay, so I will skip this of that, and the way I talk about is from the algebraic eigenvalue angle. But some other formulation also can looking at it from the eigenvalue optimization, etc. So that's all strictly Lagrange multiplied optimization problems, etc. So my last topics, or my third topics, is about the third types of eigenvalue problems. It's called eigenvector dependent nonlinear eigenvalue problems, MEPV. Okay, so just like this. So although this is seemingly, of course, more complex than the previous two, but it's also pretty straightforward to define it. We call it, this is called the standard. I call it the standard nonlinear, because you can more generalizing introduce another matrix on the right hand side, etc. So essentially, you given a Hermitian matrix, but this matrix is going to depend on this vector v. Okay, it's a part of the v defined. You will see example later. Okay, I showed you earlier already how they're dependent. But nevertheless, you're basically looking for such a vector and a bunch of vectors and satisfy this eigenvalue equations, eigenproblance equation. You can also make some assumption, because this, once you have a space V, a bunch of vector, it's always related to how they're going to change it within the orthogonal changes, etc. You can making some assumption about the so-called unitary invariant set. But some of those properties have some recent study review that this might be a more general sufficient, because many other types of formulator can redefine to satisfy this type of homogeneous. Okay, so this is the basic. And also last one, because this, if you're looking at this, all those eigenvalues you are typically looking for these matrices, because there must be corresponding some eigenvalues of this. So in physics, in quantum physics or chemistry, Ponshan equation, they're typically looking at the smallest bunch of eigenvalue, etc. But a recent study also revealed from some of other problems, they may not be corresponding of that, because the corresponding so-called the smallest eigenvalue has some physics background. They call it off-half principles, but in general, they call it some other types of definition. For example, as I show you, is a Constant. This is single particle Hamiltonian. As you can see, this is a notation. This is just this matrix. It's called a projection matrix. You take its diagonal elements, and then this become a vector. So this is called a density matrix. If in case density is not a density matrix, this is projection matrix. This is density, and then you doing this clinical. This is Laplacian is representing the clinical energies. So this is the one type of the eigenvalue. You can also in a real physics computation, this HV is way complex. It has multiple terms. But essentially, you can think about it. This first term is just the kinetic energy of system. All those rest of terms are associated with pseudo potential. Okay, coming from like this Hartree pseudo potential, this is exchange correlation potential, etc. But it doesn't matter of that. Just to think about this is a form of this. And you can also think about, for example, there is a TensorFlow, the tensor work of that. You have certain tensor, there's certain symmetry, you're looking for optimal lower rank approximation, or sometimes they also define as so-called C eigenvalues of tensors, etc. As you can see, once you reformulate this optimization will equivalent to optimizing this province, and later you will see this optimization problem essentially need to solving this algebraic eigenvalue problems. And here the Hx is just all this coefficients matrix term, etc. And also other things we also study a lot in recently is in typically when you consider Rayleigh quotient, you always think about it as a constants matrix. But of course, in the reality, all those matrices depend on certain parameter. And this certain parameter may changes between a certain range. For example, in this so-called brain-computer interface (BCI) systems. So this is the electronic signals called EEG. You measure the brain waves, etc. So you will find that they're always subject to certain noise and etc. So therefore, you are looking for minimax such a so-called Rayleigh quotient of that. Later you will see with the proper assumption of these variables, which range they are changing, etc. It will formulate this nonlinear Rayleigh quotient, because in this case, we call it this G and H now, depend on the eigenvector you're looking for. And this eigenvalue problems and also eventually leads to this types of nonlinear eigenvalue problems of that. So of course, here it's a lot of work are all related to this class of this. Recently, there's a very nice survey article just published on the Science Review regarding particular types of this called Bose-Einstein condensation and this Gross-Pitaki equations, and people systematically study how to associate with this nonlinear eigenvalue problems of that. So, and then so in the last 5, 10, more than roughly 10 years now, if not 10 years, at least 8 years, because Cai Yunfeng was still study eigenvalue problem, but now he's no longer doing that. But at that time, we started we systematically looking at this problem. We started answer some of very basic questions. What are the existence, uniqueness, and what are the fundamental types of that? So first, we're looking at existence. So we made an assumption. One is sort of like a Lipschitz type of condition. The second is about the sufficient gap. Okay, they call the uniform well-postedness. That's a physics term. So we can show under these two very genetic assumptions, you can guarantee such a nonlinear eigenvalue, the solution exists. Okay, so that's At least by my knowledge, this is still the latest results, although we published in 2018. So, and of course, you can using this to apply it to different systems to illustrating what the meaning of this assumption. Although, for example, like in this case, we have to assume that there is a spectrum gap at this scale. And of course, this is way pessimistic in a real physics, particular metallic systems. So this gap is way too big to guarantee for the uniqueness. So therefore, certainly that will be interesting how to make such assumptions and become more realistic, particularly you have such a structure exist there. The other problems you study eigenvalue problem, as I already show you in linear eigenvalues. This is essentially I show you in a linear eigenvalue problem, is right. Either you are looking at the smallest and or largest, you can using this really caution to characterizing them. So in the matrix theory, this is using this term so-called a variational characterization. Basically, through this variational form to do this. So of course, you are naturally asking this question. What are the nonlinear eigenvalue problems you talk about? So this is the nonlinear eigenvalue problem that I'm talking about, is right? So how to define, or what's the appropriate variational characterization quantity should look like? Because over here, for linear case, that's we all know, is right? You all taking the matrix the courses, linear algebra, you learn in the introductory linear algebra. So here is a general way of thinking. Although practically you have to deal with in it. It's basically you can start thinking, I have an objective function which is defined by x, but x is living on this also a mathematical term called a manifold or Stiefel manifold, because they have to be all orthogonal, etc. of that. So essentially you can just say it's just a standard optimization with orthogonal constraint, because that's a constraint you need to impose. But of course, you can use KKT or using the take gradients of this plus constraint using Lagrange multiply method, or you are using so-called Riemannian gradient on this manifold. This is over here also called a Stiefel manifold. You can find if the gradient has to be in this form. This is again just you study, you looking at that, you immediately know that's not surprising. Then the H here, this is just a regular of this. So of course, if you wanted to find a great optimum of this, you have to satisfy KKT condition. So in other words, gradient has to be equal to 0. And once you're equal to 0, basically this hx term has to be equal to x times all those terms we call the capital lambda. In here, lambda, the specific form, it doesn't matter. It's all just to say it has to be symmetric. Okay. So now, as you can see, if I assume hx can be partitioned into some hx hat times x and equal to this right-hand side, then I essentially solving these KKT conditions is equivalent to solving this nonlinear eigenvalue problems. That's basically is that. Of course, you have a fundamental question you have to ask. Okay, so this is just the first two bullets just to show where the background we can skip. Essentially, you have to asking, because you are looking for optimal of this objective function fx, then you have to asking for this h. Now, if you consider the hx, but you are consider this hx here, or hx here, you have to asking which part of this should be h hat. Okay, so which part of this matrix will associate with your optimal x? Okay, so this is that question. And so, of course, in our general definition, I just say you're looking for this hx is the smallest or largest. But it turns out for some optimization problem, they may not be. They may not be the smallest. They may be second smallest or something. Then of course, you can also similarly asking, because in the reality, you always construct a sequence of approximation. Then you need to guarantee this objective function has to be monotonically increasing. Is right? Because you're looking for maximizing of that. You need to do this. Of course, you can also need to addressing what if my hx cannot be written in this form, and what's going to do, etc. So those are the very general types of problems you can associate within if you want to study so-called variational characterization of this type of nonlinear eigenvalue problems. And people are working on this and making quite a bit of progress. So for the time being, I just quickly show you two examples. For example, one of the nonlinear eigenvalue problems like this, okay, because this is form of a matrix, and this is a function of really quotients. And then you can show associated eigenvalue problem, just you can study of optimization problem like this, and which is coming from very different applications. And then you can show this nonlinear eigenvalue problems within this, and assume this hi, the equivalent derivatives of this, and then within the sum of that, you can show if you find optimum of a local optimum, you essentially find eigenvalues. And all you find eigenvalues, eigenvectors, you are solving the optimum. In other words, this is completely characterizing in terms of this, you in turn using this optimization problems, or vice versa, because that's exactly the spirit of our classical of that. And of course, you can see it's really a generalizing the form of what you saw here, because that's a linear algebra textbooks of the results. The other more, this is more by Zhang Leihong, etc. He studied long ago, published. He can show such a really quotient types of this essentially lead associated within this. But then there is a much more recent work when by Yunfeng, etc. They study this. You can also change this instead of constants. They can also depend on the eigenvector, and this is associated within this type of linear characterization. And so in terms of algorithm, so I will try to finishing up in 2 minutes of that. In terms of algorithm, there's, as you can see, lots of algorithm has been looked into from the classical of method. But most basic method probably is so-called self-consistent field iteration. It's just like a power method, and because as you can see for linear eigenvalue problems, the power method is the most basic methods. And over here, essentially, you are using this so-called self-consistent, because this matrix depends on the eigenvector you are looking for. And then you can assume I will initial guess I will have a matrix, and then I solve linear eigenvalue problems, etc. But instantly you are looking for what's the background of such a, what's this simple, this called SCF iteration. What is this doing? Because if you remember when you study power method or really quotients or conjugate gradient, we're always looking at what's the gradient directions, or what's the of each power iteration when you multiply the matrix A, how will you through the mapping each times of mapping, and eventually the convergence to the eigenvector you are looking for. So this is essentially the of that. So we need to what's the when we are trying to understanding this very simple structure, and it turned out structure connection within another branch of mathematics is so-called of a joint numerical range. Essentially, all you are doing is that you can reformulate this SCF as doing optimization on this joint numerical range. Essentially, you are looking for your solution each time on the boundary. Eventually, when the gradient and projected normal direction are matching, then you have this so-called convergence. I think this is a very interesting of interpretation in terms of geometry. And of course, the convergence has lots of analysis. And so people study this as early as once they're proposing this type of method. But until recently, we are still working on one more paper. Hopefully that's the last paper we've written on this, etc. So after that, I talking about some local. I think for the time being, I will skip all this. So here is a picture. Is to show you you even for this, if you want to study this nonlinear behavior, you can study focusing on nonlinear. Only depend on one parameter. You probably this is simplest nonlinear. This type of nonlinear eigenvalue problems, and then you can using this alpha as a say because this alpha show you it's a convergence, very rapid converging to until the divergence if the alpha is sufficiently large. Then how you can use your so-called local optimally estimate, exactly predict what's the rate and whether they're going to convergence, etc. So a few years back, this is the best results, the blue line. But today we get this red line, and one is theoretical, one is red. So essentially they're matching almost on top of each other. So this is a so-called, we believe this is might be the optimal of a solution to this. And then there's a lot of other types of that. So finally, I just show you some of it, but I don't think this is all of that. So anyway, so I probably should stop here. My summary is very simple. So basically, just to say it's a very deep connection with many branches of mathematics. And so, for example, I did not get the time go into the joint numerical range and those issues. Once you get into this and associated with a lot of algebraic of a theory study, etc. So, and just like Wilkinson said that earlier, it's posing a lot of challenging. Of course, the MEPV is relatively a new topic, and there is a much more unknown open problems in that topics. I think that's all I wanted to say. Sorry, I take a.
Thank you, Professor Bai. Very exciting. Any questions?
Yes.
Yeah, so you were making some simplifying assumptions at the beginning about the absence of zero eigenvalues, and it looked to me also about non-degeneracy of eigenvalues.
Yeah.
So in the presence of symmetries,
yeah,
there can be both degenerate, I mean zero eigenvalues, and also degeneracy.
Exactly.
Can you comment about convergence and numerical stability in
yeah.
these cases?
So this is essentially you talk about this during the SCF interpretation. Okay. Yeah. Exactly. Okay. So in this study, maybe back to the very beginning of definition. So what's the this asking? Just a recap for students to understanding of this background. So let's just back to very beginning of this problem classification. So, okay. So you're concerning about B, is right? The matrix B. Yeah. For example, there is a situation if matrix B is just a singular itself, or it's very ill conditioned, and then you have to handle the such types of that. So yes, even in the classical sense, you have to handle. There's essentially two types of way to handle them. One is if your matrix are relatively small size, we talk about let's say at order under 10,000, you maybe use 10,000 as a threshold because we talk about the normal laptop computing today can handle such size. So you can using the so-called property deflation. You can using the deflating of such a so-called bad space because the difficulty is when A and B they have a common null space, and then you any eigenvalue is eigenvalue. If you use QD algorithm, MATLAB or LAPACK, it's give you very weird number, even you don't know whether it's an eigenvalue, etc. So there is a so-called of a deflation scheme. It's called a fixed Heidelberg method. I do not know whether you know they heard of this method before. So essentially, through the step of the reduction to review such a common null space. although not rigorously proved, but most cases it works. And then you can figure out this deflating the normal common norm space and then computing. So that's the one.
Yeah, so I just more curious because you've now managed to prove the conversion.
Oh, yes. Oh, this is of course has to be under that rigorous assumption. We are not be able to handle that practically. Okay, that's basically all that. So I'm more answer the other side. This is still because of that. Because as you can see, the rigorous proof of that scheme are really under this assumption of well-postedness. Yeah.
In the real world, you hear about.
Yeah, that's but if you say that in the real world, we also don't use single vector. We prefer use multiple vector. That's also, but it's very difficult. As I say, here has an expert sitting in front of you. He is a local. He also written a paper trying to prove the convergence of such scheme. Yeah, it's very fascinating. People widely used, but no mathematical guarantee. Thank you for the question. Yeah.
Okay, any questions? Due to time constraints, let's end here. So
Okay.
let's thank Professor Bai again.